All right, good morning, good afternoon, good evening, wherever you're at. Hope you're doing great. About to get into, actually, we're starting a chapter on trigonometry. Okay, that's where we're headed towards, okay? And what I want you to know, and I'm going to continue to restate this because I get this question every year, where did trigonometry come from? Because it's fascinating, okay? There's stuff that we've been working on over the course of this year, stuff that we're going to work on the next couple of days, and you're like, this is kind of difficult. Then all of a sudden, trigonometry makes it so much easier, okay? So we will get to that point, but I need you guys to follow me so you understand the process to get there. So basically, many years ago, the Egyptians started realizing that within right triangles that were similar, the angles were the same. And so through these, how do I want to say, these ratios of side lengths, they were able to say, hey, if this side here and this side here have this ratio, this angle here has to be a certain degree, okay? Now I know that's really vague, but I will expound on that just a little bit as we move into the basic trigonometry that we'll cover this year. And like I said, it's really simple. So don't be intimidated by the term trigonometry. So as we take a look here, let me pull up the screen and we'll start looking at some things that will lead to that point. The first term that I want you to know or realize is this word geometric mean, okay? So I want you to write this down. This is my dumbed down version of what geometric mean means, okay? Because you can look it up on the internet, it's a little more complicated, but basically it's the central number. Okay, so we think of mean as the average, right? And here's what I want you to think of. It's the central number in a geometric sequence, okay, or geometric progression. Now, if you remember last year, a geometric sequence was when you had a number and you apply that number, a factor to that number. So if I were to go 2, 4, 8, 16, 32, you would say each number was multiplied by a factor of 2, okay? It's not an arithmetic sequence where I'm adding the same number each time. It's where I'm multiplying the same number each time. So as we use an example here of I wanted to say, hey, here's an example. You have a number 3, you have another number, the central number, and then you have a number 27. And the question is, what number is that right there, okay? Well, there's two ways you can go about figuring that out. You can either figure out what each number, what factor was applied to each number to get to 27, or you could go ahead and set it up as a proportion, and it kind of is alluded to right here, okay? If you know the first number and the last number in that geometric sequence, the middle number can be found by this cross product here, okay? So if I were to do this as an example, something like that right there, okay? And if we cross multiply, here we have x squared, 3 times 27, 81. And if you square root 81, this is 9. And what is the common factor? Well, they're each being multiplied by a factor of 3. 3 times 3 is 9. 9 times 3 is 27. 9 was the central number there, okay? So they're going to use that term in some of the theorems that we'll look at, and I'll explain those theorems because those theorems we are able to use as shortcuts on some of the stuff we're going to look at. But for right now, I want to talk about something that you can always rely upon to get the values that we're looking for. So let's look at this first one, very simple one. We want to find the geometric mean between the pair of numbers. Okay. So as we look at this, I'm going to go ahead and do something like this. And we're going to start out the exact same way we did before, okay? Now, the only difference between this problem and the last problem that we looked at is this. As I multiply 20 by 12, we get that. And the square root of 240, unfortunately, that's not a perfect square. I'm thinking 14 squared is 196, 15 squared is 225, 16 squared, off the top of my head, I think is 256, okay? So it's somewhere between 15 and 16, okay? So how would I go about simplifying this. Again, we want to remember how to simplify radicals. I wouldn't say this is the most important thing for this year, but I know in Algebra 2 and moving forward, you better know how to simplify radicals, and it's not very difficult. So one thing that I would look to do is I might go ahead and do 24 times 10. That just seems like the logical progression here. Now, 24 times 10, let's see here. If I was to break that down, that would be 12 times 2 would be 24. So 3 times 2 is 6, times 2 is 12, times 2 would be 24. Okay, so there's 24 times 10. Okay, if you multiply each of those numbers out, you're going to get 240. Okay, and so from here, if I go ahead and pull this out, we have the square root of 4, which is 2, the square root of 4, which is 2. Now pay attention to this. We have two 2's out here. Do we add or multiply them? Well, since they're all multiplied underneath the radical, they're still multiplied outside of the radical. So in the end, we have 4 on the outside, and we have 5 times 3 left on the inside. And that number right there is the simplified form of that, and that's the geometric mean between 12 and 20. Okay? And so, obviously it was a lot easier when we had 3, 9, 27, okay? But we don't want to stick with easy. We want to make sure we know the complicated as well. So taking a look, let's see here. Yeah, so I think that's pretty good there. Next thing we want to do is we want to look at one of these two problems down here, okay? Now I'm going to pause for just a second here. Okay, so what I'd like you to do for homework, one of the problems is going to be number 2. Just do that one for me. Figure out the geometric mean between those two numbers, okay? And we'll talk more about why the geometric mean is important if you want to do a shortcut, okay? We'll do that more come probably the next time we talk about this, okay? So taking a look at number 1 down here, what is important to understand about this problem right here? Well, what I want you to see as we look at this problem is that we have 3 triangles in there. I know I've mentioned this probably before in the fact that these triangles are going to be similar to each other, all right? And so what I'm going to do, and I don't know, I'll show you 2 different ways that you can go about doing this, and then I'll let you guys choose what you want to do as far as how you want to set things up. So one way, and I'll just do it this way for this problem, and then on the next problem I'll show you a different way. One way is to go about drawing it all the same dimensions. So if I go ahead and draw something like this, okay, here's my big triangle, and label those 3 sides, A, C, and B. Okay. Now I'm going to draw a small triangle and a medium-sized triangle right underneath this. Okay, with the same perspective or same orientation. Oh, that was bad. There we go. Okay. Now from there, if I label those vertices correctly, this is again the tricky part, especially when you draw it with the orientation like I've done here. Okay. What I know is that in the small and the medium-sized triangle, D is the right angle. Okay. I also know that angle A right here is the same angle in the small triangle. So that is angle A in the small triangle. Okay. I also know that angle B is the same angle in the big triangle as it is in the medium-sized triangle. So this has to be angle B. And then from there, I know all 3 of these triangles will be similar by angle-angle similarity. Okay, based off what I'm seeing here, I've got 2 angles here to here, 2 angles from here to here. And so if these 2 angles are congruent to these 2 angles, the third angles have to be congruent as well. Likewise here. So that one. Okay. So we have ADC, so ADC, and we have BDC, BDC. Okay. So I know that was fast, but I hope you're picking up on how I labeled those angles and put it into play. Now, I am going to write a similarity statement here, so it would look something like this. If I do ABC, sticking with the alphabet, okay, A, B, C, I would have to do A, C, D in the same manner. And then you'd have to do C, B, D down here. Okay. Now what I want you to recognize here is that each of these triangles has in almost all the cases. Now there is one special case if you're working with a 45, 45, 90 triangle. This won't be true. But in almost all the triangles we work with, there will be a short leg, a long leg, and a hypotenuse. Short leg, long leg, hypotenuse. Short, long, hypotenuse. Okay? And if that's the case, when I go to set up proportions, it says here, write 3 true proportions. Let's say I use, I'll label these triangles. Triangles number 1, number 2, and number 3. Okay? And so if I want to look at 1 and 2, a proportion I could use is maybe AC is to, let's say, AD. Okay, notice how they match up within these 2 triangles. As, and maybe I'll choose the hypotenuses here, AB is to AC, okay, AB to AC, all right. So what I've matched up is short leg is to short leg within the 2 triangles, hypotenuse is to hypotenuse. That's one proportion that would be true. Okay, it doesn't matter what the expressions are, I can plug it into that and solve. What we have to be careful on is making sure that we don't have too many variables in the same proportion. Okay, you can only have one variable in the proportion. So maybe I'll go down to triangles 2 and 3. Maybe I want to say something like AC is to CB. Okay, those hypotenuses there. And maybe we'll compare that to the longer legs. So DC here to DB. Okay, again, all I'm doing is matching up corresponding parts. Okay. One last proportion that we could set up, like I said, there's multiple proportions, okay? Lots of different variations. I'm just choosing 3 so we get understanding that we can match up between triangles 1, 2, and 3. It doesn't matter which ones we choose, okay? So maybe I'll go with triangle 1 and triangle 3 on this last one. If I go ahead and say something like this, AC is to CD, okay? The short legs of the first triangle and the third triangle is to CB, which is to DB. Okay, so again, AC is to CD as CB is to DB. Okay, we're just matching up those corresponding parts right there. All right. So I hope we have a good understanding. Whenever you have what we call an altitude to the hypotenuse, that would be this length right here, the altitude to the hypotenuse, it divides this right triangle into 3 similar triangles, and we just showed that there. Once you have 3 similar triangles, you can use any variation of them to figure out how to solve for unknown parts. Okay? And that's the thinking that we want to get into. Now, you may be thinking to yourself as I transition to the next problem, how does this fit into trigonometry? Well, like I said before, when I discussed about the Egyptians and finding these common places, basically they looked at all these right triangles and they said, let me pull this out here. I see a ratio of, let's say, 3 to 5 forms a whatever degree angle here, all right? Well, if this is in the same ratio over here with these 2 side lengths, that means that this angle here has to be the exact same, okay? So when we build on trigonometry, it's all based on the fact that these right triangles are all similar, okay? So we're just trying to make sure that we've got that down. So in looking at number 1, here's how I would go about doing something like this. I'm going to redraw these separate, but this time I'm not going to draw it with the same orientation. I'm going to draw it with a different orientation. And here's what I'm going to do. I'm going to do A, B, C, and D. Okay? And so I'm going to redraw the big triangle. This is A, B, and C, and I know that this length is 4. Okay, and we'll label that triangle number 1. Okay, I'm just going to take this right triangle right here out and bring it straight down. And this will be A, D, and B. This is X, and this is 1. Okay, I might even mark out that this is the same angle here and here. Okay, so I hope that that's making sense to you so far. I'm going to take this medium-sized triangle out, and I'm going to draw it over here. And that's going to be B, D, and C. Okay, so this is X, and this is 3. All right, and I'm going to, again, label this number 2, and we'll put this one as number 3, the third triangle there. Okay, the other thing I would show you, this angle is the same as that angle, which would make this one the same as this one, and this one the same as that one. Okay, so as I look at this problem right here, okay, here's what I'm seeing. Here's my short leg, my long leg, my hypotenuse. Short leg, long leg, short leg, long leg. Okay? What you see here is this. This triangle right here doesn't have enough information. But in this one, I can compare short leg to long leg, and then short leg to long leg. And that will allow you to solve for X. So if I do something like this, short is to long, as short is to long, we can go ahead and cross multiply and solve for X. Okay? And so as I do that, we end up with X squared equals 3. And if I square root 3, that is your value of X. 3 is prime. It can't be broken down. The only factors are 3 and 1. And so that is your value of X right there. Okay? Now you actually discovered one of the theorems that is referenced up above. We'll talk more about this the next time we talk about this section. But if you notice here, there's a geometric mean here, right? And that geometric mean is this altitude. This altitude is the geometric mean between the parts of the hypotenuse that it breaks up. Okay? And so if you want to take that, you know, and you can remember that, use that. If not, just draw the pictures, match up those parts, and you can go from there. Okay? Let's do this last one together. See if we can do this. Again, I'm going to go ahead and label this A, B, C, and D. And what I'll do, actually, you know what? I'm going to clear this off before I do anything, clean this up. Okay? A, B, C, and D. And I'm going to draw it in the exact same way that it's shown in the picture. So here's what we have. All right, we have Y, Z, and we have 7. Okay, the 5 plus the 2. All right. Now the small triangle, again, I'm going to try to draw it with the orientation that's got there. Looks something like this, if my marker will work. And the vertices of that small triangle are going to be A, D, and B. Okay, now remember, this angle at A is the same angle there. Okay. Now for the medium-sized triangle, we're going to go here, and we're going to go here, and we're going to go here. Okay. And again, remember this angle at C is the same angle here as here. Okay. Now I can go ahead and reference this angle here. Has to be the third angle. Has to be the third angle. Okay. And I should fill in the side lengths too. So let's make this 2. Let's make this X. Let's make this Y. This will be X as well. 5, and Z. Okay. Now I'm going to be honest with you. One of the hardest things to do is to go ahead and identify that first proportion. Because once you have that first proportion, you can start to build off of that. But the hardest part is to find that first proportion. So if I was to go ahead and do something like this, maybe it would be best, let me change colors here. It might be best to go ahead and say, hey, this is the short side length. This is the hypotenuse. This is the long side length. This one's the short side length. Okay, again, I'm basing everything off of what I'm viewing on my picture there. This is the long, opposite the right angle, hypotenuse. This one would be the short. This one would be the long. This would be your hypotenuse. Okay? So we're just trying to get a basic feel. We don't want to match anything up incorrectly here. So maybe I'll take these first two triangles, this one here, and start to see if there's something I can match up. So one of the things, maybe I'll try the long leg. If I do the long leg is to the long leg, I know that falls apart right from the get-go because we've got a Z and an X in the same proportion. So that would not be a proportion I'd want to set up. Okay? Let's try the Y. If I do short leg is to short leg, as let's do hypotenuse is to hypotenuse, that looks like it works. Okay? We would have a proportion we could solve for Y. Let's try, let's just go ahead and use that. There's lots of different ways we can set these up. For example, if you would have went this triangle and this triangle and tried the Y value, short leg is to short leg, oops, that falls apart, right? It doesn't work because the Y and the X. If I would have done the long leg is to the long leg, as the hypotenuse is to the hypotenuse, that one also would have worked, okay? So it's just a trial and error, basically. If I look at the last two triangles, if I would have started with the hypotenuse is to hypotenuse, that falls apart, too many variables. If I do long leg is to long leg, as short leg is to short leg, that would work, okay? So let's kind of start to work some of these out. I want to start with the Y and the Z because this alludes to one of the theorems up above. So if I go ahead and do, I said short leg is to short leg, Y is to 2. And then I go up here to hypotenuse is to hypotenuse, 7 is to Y. What do we see right here with this proportion? That's another geometric mean, right? If you invert it, maybe I should have done 2 is to Y as Y is to 7, but it's the same format. That's a geometric mean. So up above, they talk about that the leg of the big right triangle is the geometric mean between the segment that it's adjacent to and the entire hypotenuse. Okay, so this segment here and the entire hypotenuse. It might be worded a little bit better up above. I'm going to talk about that the next time we get together. Okay, so if we finish this off, 7 times 2 is 14. We have Y squared. I'm going to square root 14. Now the factors are only 7 and 2. Okay, I can't break anything else apart. So this is my final answer, the square root of 14. Okay. Now technically, if you have this number, you can go ahead and solve for Z using the Pythagorean theorem. Okay, and I'm okay with that. But make sure you do it correctly. Sometimes the proportions are easier than using the Pythagorean theorem. If we move on to, let's say, Z, okay, what do we say for Z? We could use, let's do long leg is to long leg, as hypotenuse is to hypotenuse. That also works. So what I say, Z is to 5. Actually, let's do 5 is to Z. Long leg is to long leg, as hypotenuse is to hypotenuse. Okay? Again, I have another geometric mean, right? So we have a leg of a right triangle is the geometric mean between the segment it's adjacent to and the entire hypotenuse. Okay? And so as I work this out, Z squared equals 35. If I square root 35, the factors of 35 are just 7 and 5. They are both prime. So this is your answer for Z. Okay? For the last one, we said something like this. Long leg is to long leg, as short leg is to short leg. Okay? Again, you see a geometric mean right here that we just talked about. The altitude to the hypotenuse is a geometric mean between these two segment lengths. And so if I cross multiply, x squared equals 10. The square root of 10, the factors are just 5 and 2. Nothing to be factored out. So that is your answer right there. Okay? So I hope that, it's not the easiest concept there. It's not earth-shattering or anything like that. It is what it is. It breaks it apart into 3 similar triangles, and we just have to match up their corresponding parts. So what I'd like you to do, from the very first section, as I said before, I wanted you to find the geometric mean between those two numbers. And then I'd like you to do number 3 from this section right here. So you've got 2 problems for the next time we get together. If you have questions, come back and talk to me. I'd love to help you out. Otherwise, I will see you the next time I see you. Have a great night, folks.